motor control is the cornerstone of automation, enabling precise movement and operation of machinery. At its core, motor control involves regulating the speed, torque, and direction of electric motors. This is crucial because motors are the driving force behind countless industrial and domestic applications. To truly master motor control, you need to understand the underlying principles, such as the interaction between voltage, current, and magnetic fields. This knowledge allows you to optimize performance, increase efficiency, and reduce maintenance costs. As we dive deeper, you'll learn about the different types of motors, their specific control requirements, and the advanced techniques used to fine-tune their operation. Understanding the physics behind motor control is crucial for mastering automation systems. At its core, motor control is about manipulating electrical energy to produce mechanical motion. Imagine a motor as a complex dance between electrical and magnetic fields. When you apply voltage to a motor, you're essentially choreographing this dance. The current flowing through the motor's windings creates a magnetic field, which interacts with the magnetic field of the motor's rotor, causing it to spin. This interaction is governed by the principles of electromagnetism. The speed and torque of the motor are directly influenced by the voltage and current supplied. Higher voltage increases speed, while higher current increases torque. It's important to note that the efficiency of this process depends on the motor's design and the quality of the control system. For instance, using an autotransformer to vary the voltage, as mentioned in the context, allows for stepwise speed control. However, modern systems often use more sophisticated methods like variable frequency drives, VFDs, to achieve smoother and more precise control. To configure your motor control system, start with the power supply settings. Ensure your voltage is set to the motor's rated voltage, which is typically 230 volts or 460 volts depending on the motor. Next, adjust the current limit to prevent overload. For a 3 horsepower motor, set the current limit to approximately 10 amperes. Now, let's talk about the frequency settings. For a standard 60 Hz system, maintain this frequency, but if you're working with a variable frequency drive, you can adjust this to control motor speed. Remember, changing the frequency directly impacts motor performance, so precision is key. Lastly, configure the motor's thermal protection settings. Set the thermal trip point to 150% of the motor's rated current to safeguard against overheating. This setup ensures your motor operates efficiently and safely. And here's why that matters. To execute motor control techniques, you must understand the nuances of the motor's behavior under different conditions. For instance, when adjusting an autotransformer, you're essentially varying the voltage supplied to the motor. This changes the speed and torque characteristics. Imagine a large industrial press from the late 70s, driven by a massive single-phase railway motor. The speed was controlled by tapping into different points on a large autotransformer, which also boosted the voltage from 380 volts to a maximum of 650 volts. This setup was extremely reliable, requiring no maintenance for years. But there's more to it. You must also consider the motor type. For a DC motor, varying the voltage through an autotransformer changes the armature voltage, thus altering the speed. However, for an AC motor, you typically use a variable frequency drive to achieve smooth speed control. The key is to understand the specific motor's requirements and the implications of each control method. Diving deeper into motor control, let's discuss advanced techniques and optimizations. Consider the use of vector control, also known as field-oriented control. This method allows for precise torque and speed control by decoupling the magnetic field from the torque-producing current. To implement this, you'll need to calculate the dq axis components of the motor's current. Set the d-axis current to 0 to eliminate the magnetic field component, and adjust the q-axis current to control torque. Remember, the key parameter here is the motor's inductance, which you must measure or obtain from the datasheet. Another optimization is using sensorless control algorithms. These algorithms estimate the rotor position without physical sensors, reducing cost and complexity. The trick is to use high-frequency injection methods to detect changes in the motor's inductance, which vary with rotor position. Be aware, though, that sensorless control can be less accurate at low speeds, so consider using a low-speed sensor-based fallback. One of the most common pitfalls in motor control is improper calibration of the motor parameters. Imagine setting the motor's speed without correctly calibrating the current and voltage limits. This can lead to overheating and eventual failure. Another frequent issue is the incorrect selection of motor type for the application. Using a universal motor where a stepper motor is required can result in inconsistent performance. To avoid this, always verify the motor specifications against the application requirements. Also, be mindful of the environmental conditions. Motors operating in high-temperature environments may require additional cooling solutions. Lastly, ensure that the motor's feedback mechanisms, such as encoders, are correctly installed and configured. Misaligned or improperly configured feedback can lead to erratic motor behavior. Remember, the devil is in the details when it comes to motor control. To master motor control, remember the key parameters and values we've discussed. Set the motor's voltage and frequency according to the specific requirements of your application. Use variable frequency drives for precise control, and don't forget to calibrate your sensors for accurate feedback. Anticipate potential issues like overheating by monitoring current and implementing protective measures. Lastly, always keep an eye on the system's performance metrics to ensure optimal operation. By following these steps, you'll achieve efficient and reliable motor control. And if you want to dive deeper into these concepts and more, make sure to subscribe to our channel for continuous, high-level education that's completely free.